Good morning, students. Today we start our class with lipids, especially for Pharm D students, pharmacognosy and phytopharmaceuticals, in which they have given very clearly about details about oils. Last class we had a discussion about the volatile oils and especially essential oils and different examples also we have seen. Now we are going to, according to the syllabus, it is about lipids. Especially we want to know about some definitions, and then we have to go certain analysis how they are doing for lipids, and selected examples which are very commonly used in pharmaceutical applications. And these structures which I have shown taken is there will be some liposomes, phospholipid bilayers, which I want to just to show this picture not with some relation background, stating that we have now formulations which are more advanced and which patient is to prefer, even like transdermal, sustained release, and various liposomal particles like nanoparticles preparation, encapsulations. These all are some of the advanced formulations which we can see in pharmaceutical industry in present days. So that's why I took this picture to show you how the liposomes and the phospholipid bilayers and these layered of formation by lipids have been utilized for various release of drug in pharmaceutics. Lipids are broadly defined as any fat soluble lipophilic naturally occurring molecule such as fats, oils, waxes, cholesterol, sterols, fat soluble vitamins such as vitamin A, D, E, and K, monoglycerides, diglycerides, phospholipids, and others. The main biological function of lipids include energy storage, acting as structural components of the cell membranes, and participating as important signaling molecule. What do you mean by signaling molecule? Here I want to say you what is this signaling molecules. Especially here we just mention about the gene or genetic engineering or pharmacogenomics, which we have studied about the gene coding and genetic engineering for various development of drugs, in which you can see the lipids plays a major role for coding, like the DNA molecule, RNA molecules, and the coding of the genetic coding, arrangements of the molecules in the gene. The signaling coding is also utilized by means of these lipids and fats of phospholipids. Although the term lipid is sometimes used as a synonym of fat, fats are subgroup of lipids called triglycerides. Lipids also encompasses molecules such as fatty acids and their derivatives, including tri, di, monoglycerides and phospholipids, as well as other sterol containing metabolites such as cholesterol. On the basis of nature of the product obtained on hydrolysis, lipids are mainly divided into two types, such as simple lipids and compound lipids. Besides, there is one more type called derived lipids. Simple lipids, lipids which upon hydrolysis yield one or more fatty acids and an alcohol. Compound lipids, lipids which upon hydrolysis yield in addition of fatty acids and alcohol compounds such as phosphoric acid, sugar, etc. Derived lipids, lipids which also do not contain any ester linkage but may be considered to have been derived from naturally occurring esterified materials. Most of this has been alcohols of complex nature. Example, certain steroids, certain vitamins and certain plant pigments. So lipids may be broadly defined as hydrophobic or amphiphilic small molecules that originate entirely on in part from two distinct types of biochemical subunits or building blocks, keto-acyl and isoprene groups. Using this approach, lipids may be divided into 8 categories: fatty acyls, glycerolipids, glycerophospholipids, sphingolipids, sacrolipids, and polyketides derived from condensation of keto-acyl subunits, and sterol lipids and prenol lipids derived from condensation of isoprene subunits. So like these 8 categories, the lipids can be divided or can be classified. Fixed oils and fats. Both fixed oils and fats are termed as triglycerides or triacyl glycerols. These are the reserve food materials of both plants and animals. The difference between fixed oils and fats is their physical state. Those which are solid between 15.5 to 16.5 degrees centigrade are termed as fats, while those are liquid between 15.5 to 16.5 degrees centigrade are termed as fixed oils. So, by this they can be differentiated. Fixed oils and fats are esters of fatty acids with glycerol. Example, triester of glycerol. Glycerol is a trihydric alcohol containing 3 OH groups which combines with 3 same or different fatty acid, long chain carboxylic acid to form triglycerides and 3 molecules of water. This is the reaction which we have explained now. Glycerol, 3 OH group react with the fatty acids, different, long, short, and triglycerides is formed by means of releasing 3 water molecules as shown in the equation. When 3 molecules of same fatty acids combine with glycerol, then the product is called a simple glyceride. When 2 or 3 different fatty acids combine with glycerol, then it is known as a mixed glyceride. You can see this reaction stating that glyceryl tristearate is a simple glyceride. You can see that after CH2O, CO, 16 CH2 and CH3, 17 carbon atom is attached molecule. Same is attached with all the 3 CO carbon atom or CO functional group, or as an ester linkage, all of them are same molecules. That's why it is simple glyceride. But if you see in the second structure, here it shows CH2 14 and CH3. Next one is CH3, CH2 12 and CH3. Third one is olefin, double bond is there, CH2 7 times CH, double bond CH, CH2 7 and CH3. So all the 3 are different esterification, different mixture of glycerides. This is called glyceryl palmitostearoleate ester, which is mixed glyceride. Fatty acids are carboxylic acid with a hydrocarbon side chain. These fatty acids bear even number of carbon atoms. Generally, natural fat containing fatty acids with 14 to 24 carbon atoms. Fatty acids may be saturated or unsaturated. Again, there is 2 categories. Saturated fatty acids, they do not contain any double bonds like this. They do not have any double bonds, saturated fatty acids. But unsaturated, the second structure, you can see there is a double bond. So that's also single double bonds containing compound, 2 double bond containing compound, and 3 and multi double bond containing fatty acids are also available. So these contain 1 or more double bonds. When it contains a single double bond is present, then it can be called as monounsaturated fatty acid. And are called, and sometimes if there is more, like they are called as polyunsaturated fatty acid if multiple double bonds are present. PUFA, polyunsaturated fatty acids. So here, examples of saturated fatty acids, you can see butyric acid, which contains CH3, CH2, twice COOH and 4 carbon atom, which is present in butter fat. Caproic acid, CH3, CH2, 4 times COOH, 6 carbon atom. Melting point is minus 2 degrees centigrade. It is present in palm kernel oil. Caprylic acid is present in coconut oil origin. Capric acid is present in palm oil. Lauric acid is present in coconut oil. Myristic acid is present in palm oil. Palmitic acid is present in arachis oil and sesame oil. Stearic acid is present in arachis oil and sesame oil. The tabular column denotes the number of carbon atoms with melting points. For your reference, it's needed for you to have an idea about this saturated fatty acids examples. When come to unsaturated fatty acids, you can see there is a single double bond, that is palmitoleic or palmitoleic acid present in cottonseed oil, 16 carbon atom. Oleic acid, in 9 and 10 there is a double bond which is present in corn oil, sunflower oil. And linoleic acid, which contains 2 double bonds, sesame oil and sunflower oil, it's present in sesame oil and sunflower oil. Linolenic acid, which contains 3 double bonds in 2, 4, 6, 7 and 9, 10. You can see the structure, 18 carbon atom. It's present in linseed and the soybean oil. Arachidonic acid is present in most of many compounds, 20 carbon atom is present in many oils, not specifically mentioned. Classification again, fixed oils and fats can be classified based on their source as follows. Plant source and animal source. First, plant source, fats, these are solid temperature 15.5 to 16.5 degrees centigrade. Examples like cocoa butter, nutmeg butter, palm oil, etc. Drying oils, these oils upon exposure to oxygen harden to form a tough solid film due to cross-linking of their components. Example, linseed oil, poppy seed oil, walnut oil, etc. Semi-drying oils, these partially form a tough solid upon exposure to atmospheric oxygen. Example, castor oil, mustard oil, sesame oil, etc. Non-drying oils, these do not harden to upon exposure to oxygen. Example, olive oil, peanut oil, almond oil, etc. And now we are coming to the animal source. You can see the 2 pictures which I have shown in the slide. The one is white in color, which is a lard which is obtained from pork, and you can see the red color, slightly reddish, yellowish and white. It is from goat or sheep meat. It is possible for you to get this type of fat from animals like lard, and that is called whiting, and another one is sweet or sweat. Oils, example from animals, cod liver oil, shark liver oil, very common, which is for A&D capsules, which we are having pharmaceutically, more useful. Properties, certain properties common to both fixed oils and fats are as follows. They are greasy to touch, insoluble in water, but soluble in organic solvents like chloroform, petroleum ether and benzene. Being lighter than water, they float on the surface of water. They are non-volatile in nature and cannot be distilled. They undergo saponification reaction when boiled with alkali. The product formed in alkali salt or fatty acids termed as soups along with the glycerol molecule. Basically, saponification represents the alkaline hydrolysis of fats and oils. This is the reaction of the saponification soap formation. Triglycerides of fatty acids, when it added with sodium hydroxide, react with the glycerol and it forms glycerol, and breakdown has taken place, and or CONA. It can be long chain, and the soap is formed as a salt of sodium. Fixed oils and fat turns rancid actually. It's a common defect in all the even cooking oils in our home which we are using. Deteriorate to give an unpleasant odor. Triglycerides made up of unsaturated fatty acids are more susceptible to rancidification. And also fatty acids containing more double bonds are more likely to get oxidized by water and give unpleasant odor or rancid, and rancidification can occur very fast. Extractions. Fixed oils and fats are extracted from both plants and animal sources as the following three techniques. Rendering. Animal tissues from which fat is to be extracted is minced and heated with or without water. The fat melts, which is then suitably collected. Pressing. In this technique, seeds containing the oil are initially crushed between the steel rollers and fed into a hydraulic press. Solvent extraction in this residue left after rendering and pressing is treated with suitable solvents like petroleum ether and benzene to extract the remaining fat or oils. Identification tests. Fixed oils and fats can be detected by presence of glycerol, which is produced upon their hydrolysis. This is for general test. There will be a specific test for each and every oils. General test: 5 drops of fixed oil or fat plus 1 ml of 1% copper sulfate solution plus 5 drops of 10% sodium hydroxide solution. A clear blue solution is formed, indicating the presence of glycerol. 5 drops of fixed oil or fat plus 0.5 grams of sodium hydrogen sulfate, pungent odor of acrolein is formed. The formation of acrolein is actually for test. It indicates the presence of glycerol, but acrolein formation is not a favorable thing for usage of oil. When you go on heating the oil more and more, acrolein formation, it is a poisonous substances, may cause nausea, vomiting. One who take the preparation which is made by that particular oil, overheated oil. So anyhow, now just a minute, this one is also coming under, just I'll pull down. So you can see here, now we are going to see about the analysis, analytical parameters of oils and fats. In this, the properties of oils and fats vary along with the degree of unsaturation, average molecular weight, and also acidity from hydrolysis. A number of parameters are used for here analysis, which are include under physical constant and chemical constant. So physical constant include viscosity, specific gravity, refractive index, solidification point, etc. In this, I am not going to give you more details because because we want to know about many drugs when you compare to the syllabus of Form D. But anyhow, it's necessary for the student should know viscosity is an important parameter to identify the physical parameter for lipids. By means of Astol's viscometer, it is possible for you to find out the millipoise or centipoise of the viscosity. It plays a major role for rheology of any pharmaceutical preparation if they are lipids when you are taking and supplying in a product form. Specific gravity is one of the important factors which you have to be find out for oils. You know that gram per ml by means of specific gravity bottle, comparing with the water. Taking the weight at specific gravity bottle can be used for you to find out the specific gravity. The density can be determined. And relative density can also be calculated with comparing with the water. That's a standard. Refractive index is one of the parameters which you should know that light when passes through one medium to another medium, it has a refraction. You know that light, when a light falls on an object, it has a lot of parameters. Some of them are reflected, some of them are refracted, some of them are absorbed, some of them are transmitted, some of them are scattered. So in this case, you have to think about the refraction plays a major role to find out the quality of the oil by physical parameter can be determined by sin I by sin R. Abyss refractometer can be used. Solidification point also plays a major role for fixed oils and fats. In what temperature it gets solidified, and in what there are many other parameters also there. Slip point, fire point, spark point. Like that there are many physical parameters which can also be determined for standardization of fixed oil and fats. The students have to get a small reference for all these physical parameters. Under this group of chemical constant, conventionally the parameters like iodine value, acid value, peroxide value, saponification value, unsaponicable matters are noted. There are many. These are some of the things which we are carried out in our lab also. So just I have given some theoretical information, practical events also you have to refer so that it will be easy for you to appear in the examination point. In recent times, even gas chromatography determination of fatty acids profiles have been introduced for identification of fats and oils. Chromatography technique, you may be knowing about the chromatographic technique which can be easily used for any mixture of compounds. So it will be easy for you to determine the amount of fats, and it can be separated from the mixture of compounds. After hydrolyze, you can find out what is the acid values and also what is the value of the functional groups can also be identified even if you are incorporating gas chromatography with NMR spectroscopy or gas chromatography with IR spectroscopy. Functional groups can also be determined. At present, we have many sophisticated instruments. Chromatographic techniques can be mixed up with various other instruments, can also be more useful in standardization of herbal formulations and herbs. Physical constant include viscosity, specific gravity, refractive index, solidification point, etc. This slide just to make you to remember that is I just told you have to refer and make these things to be clear, the procedures how they are followed to standardize fixed oils and fats. Iodine value, it is defined as the weight of iodine absorbed by 100 parts of weight of sample of fats or oil. Iodine value is measure of the extent of unsaturation. Susceptibility of rancidity increases for the oil which is having higher iodine values because of higher number of double bonds, and it will be having more susceptibility of rancidification. Hubel's method in iodine value dissolve the weigh amount of sample oil or fat in carbon tetrachloride, solubilize and allow the above solution to react with iodine solution in presence of catalyst mercury chloride in ethanol. Actually, iodine solution means very simply we have written, but you should prepare in molar. Usually 0.05 molar is prepared. That's why we are using the formula. That is actually the molecular weight of iodine plays a major role for you to use for calculation. First you should know what is the molecular weight of iodine. Titrate the unreacted iodine and standardize with thiosulfate solution. That means sodium thiosulfate is the standardized solution which you have used for titration. Then perform blank titration without the sample. Difference between the volume in ml, that is the blank, and the titer value of sodium thiosulfate solution in 2 titration indicates the iodine absorbed. In this method, more reactive iodine monochloride is allowed to react with the sample instead of molecular iodine solution, which is prepared by separately with using iodine with potassium iodide. The rest of the procedure is the same. Only thing is we are in Hubel's method, we use iodine trichloride. In glacial acetic acid is used instead of the iodine solution. Only the difference. And you say, what is the significance of this iodine value? Anyhow, there is a question always asked, what is the significance of any experiments which you are performing? What is the use? It has all the demerits and merits of that particular application of any procedure which you have followed for standardization or any procedure. Significance of iodine value decrease or degree of unsaturation can be known with the help of iodine value. Drying character of oil can be determined. Adulterants can be recognized. Quantity of the fat or oil required for converting them into soap can be determined, and calculation can be made for iodine value from the expression of 1.269 into the volume. V means the blank minus titer value, difference in the ml between titration value and the weight of the sample which you have taken, the oil or the fat in grams, will be divided by the whole, the sample, and then we will find out the iodine value. I was talking about this 1.269 is a number which doesn't use written. It came from the molecular weight of iodine. If you just calculate 0.05 molar of iodine solution, how much iodine should be weighed? It should be 1.269 for 250 ml flask. To prepare a 0.05 molar of iodine solution. So that's why I told you, always whenever you are going for an assay, the molecular weight of the component plays a major role for determination. The iodine values of some fats and oils which I have given here. Iodine value for butter 26 to 28. Lard is 46 to 70. Tallow is 30 to 48. Edible oil like cottonseed oil is 105 to 114. Soya bean oil 128 to 143. Sunflower oil is 140 to 156. And non-edible oil, tang oil 160 to 175. Linseed oil 170 to 185. Saponification value, it is defined as the number of milligram of potassium hydroxide required to neutralize the fatty acid, resulting from complete hydrolysis of 1 gram of sample of oil or fat. Saponification value occurs in an inverse proportion to the average molecular weight of fatty acid present in the oil. You know that saponification value depends upon the reaction of the sodium hydroxide making the soap. This value is normally applied for butter, fat, coconut oil in which the low fatty acid glycerides occurs in high content. The calculation can be made by saponification value is equal to A minus B, means it's about the difference in the blank and the titer value into 28.05. How come this 28.05? Because here we are using 0.5 molar potassium hydroxide. This is molecular weight of potassium hydroxide. Molecular weight of potassium hydroxide is 0.106.107 divided by, that means it's 0.5 molar which you are using. That's why it is divided by 2 and then divided by 100. Divided by weight of the grams to be taken, it will give you the saponification value. Hydroxyl value, it is defined as a number of milligram of potassium hydroxide required to neutralize the acetic acid capable of combining by acetylation with 1 gram of sample of fat or oil. Acetyl value, it is the number of milligram of potassium hydroxide required to neutralize the acetic acid obtained when 1 gram of sample acetylated oil is saponified. Acetylated oil is again saponified except castor oil. Acetyl value 150. Most of the oil and the fat have low acetyl value 3 to 15. Except castor oil will have little more. Unsaponificable matter. It is matter present in fats and oil which after saponification by caustic or sodium hydroxide alkali and subsequent extraction with an organic solvent remains non-volatile on drying at 80 degrees centigrade. It indicates, or it includes sterols, phytosterols and cholesterol, oil-soluble vitamins, hydrocarbons and high alcohols. So what all it includes? Sterols, cholesterol, oil-soluble vitamins, hydrocarbons and high alcohols. Paraffins, hydrocarbons can be detected by this method as adulterants in fats and oils if they mix. Acid value is a very important parameter which you have done in your lab also. It is defined as the number of milligram of potassium hydroxide required to neutralize the free acid present in 1 gram of sample of fat or oil. Generally, rancidity causes free fatty acid liberation. Hence, acid value is used as an indication of rancid state. Acid value is equal to volume. That means if you are performing blank minus titer value of 0.1 molar solution of potassium hydroxide consumed into 5.611. How come it is 5.611? It also comes from the potassium permanganate, potassium hydroxide molecular weight 56.1. How it came? Divided by 2 and again divided by 100. Because here you used 1.1 molar potassium hydroxide alcoholic solution. Weight of the sample is divided so that you can find out the acid value. Peroxide value defined, it's referred to the number of milli units of peroxide oxygen hydroperoxides present in 1 kilogram of sample oil or fat. Procedure: dissolve the weight amount 1 kilogram of fat or oil in glacial acetic acid, add excess potassium iodide solution and titrate the resultant solution with standard sodium thiosulfate using starch solution as indicator. Reaction, you can see that is acid react with potassium iodide, potassium hydroxide and iodine reaction, and you can see iodine. You can see that because it was just, I have to pull down or I have to reduce it so that you can see clearly, because you can see now potassium iodide heated and ROH KOH plus I2, and iodine react with sodium thiosulfate and sodium iodide, and sodium thiosulfite is formed, and peroxide reaction, you can see that is S minus B into N by W into 1000. S stands for the volume of the titrant and volume of the titrant blank, and the normality of the sodium thiosulfate and the weight of the sample which is taken by you. So this is how, and you can see peroxide is equal to the, again we have written the same formula in 2 into V minus V1 minus V2, that is blank. Difference between blank and titer value in equivalent weight by kilogram by weight of the sample. So this is what the formula which we have discussed about the peroxide formula. Significance of peroxide value is used to determine the quality of the oil or fats by measuring the extent of oxidation in them. 0 peroxide value indicates that the fats or oils is of high quality. Low peroxide value represents beginning of oxidation. Oils or fats having more than 20 is said to be very poor quality. Peroxide value 1 to 5 is low extent of oxidation, 5 to 10 is medium, more than 10 is very high oxidized. Crease test, rancidity index. Due to rancidity, epihydrin, aldehyde or menonaldehyde are increased, which are detected by Crease test using fluoroglucinol, which produce red color with the oxidized fat. Ester value, it is defined as number of milligram of potassium hydroxide required to combine with fatty acids which are present in glycerides formed in 1 gram sample or oil or fat. Difference between saponification value and acid value is ester value. Very simple. Find out the acid value, find out the saponification value, find out the difference that gives the ester value. Richet-Missel value. This value is measured volatile water soluble acid content of the fat. It is defined a number of milligram of N by 10 potassium hydroxide solution required to neutralize the volatile water soluble fatty acids obtained by 5 gram of fat. Same thing, Polanyi value, it is also having number of milligram liters of N by 10 potassium hydroxide solution required to neutralize water insoluble. There and they are different. Water insoluble, steam, distillable acid liberated by hydrolysis of 5 grams of fats. Waxes now. We have to discuss about the waxes. In this case, just I have taken only the what do you mean by wax and what is the difference between wax, lipids and volatile oils are also I have taken for this consideration to be discussed in this class. It's little lengthy, but anyhow you can part by part you can listen. Waxes along with fired oil and first along also belong to the group of natural occurring compound called lipids. They differ from fats and oils as they long chain fatty acids combined with long chain monohydric alcoholic or sterol instead of glycerol. Thus, wax only a single ester group, whereas fats and oils 3 ester groups. Usually waxes are composed of unbranched carbon chain acids and alcohols. Properties: these are viscous solid substances which are greasy to touch and have characteristic shine. Waxes contain less content of unsaturated fatty acids, hence are different to saponify. Unlike fats and oils, they possess low saponification and iodine values. Waxes are immiscible in water and miscible in non-aqueous solvents. Waxes are not easily hydrolyzed. Hence they are used as protective coatings. They get hydrolyzed only with hot alcoholic alkali to yield soaps in the following manner. Beeswax can react with sodium palmitate. It can be converted into sodium palmitate and miracyl alcohol insoluble when it is reacted with sodium hydroxide. They are highly resistant to rancidification upon exposure to atmospheric oxygen. Waxes are hard in nature and their melting points are very high, 35 to 100 degrees centigrade they are compared to fat, when compared to fat. Types of waxes depending upon their sources. Waxes are classified as follows. Plant waxes. The surface of leaves, stems and fruits show the presence of wax. The waxy coating present on the surface of desert plants protects them from exclusive loss of moisture due to evaporation. It also protects the plants from being affected by harmful organisms. Carnauba wax, which is obtained from the leaves of Carnauba palm of Brazil, its main constituent is miracyl cerotate C25H51 COOC31 Hg63, which when hydrolyzed yield miracyl alcohol C31H63OH and cerotic acid C25C51COOH. The melting point of Carnauba wax is 80 to 87 degrees centigrade. It is used for floor polishes and used in automobiles due to its hard and impermeable nature. It is also coated on carbon paper and mimeograph stencils. Animal waxes, the most important function of these waxes is that they are widely used as protective agents. They are obtained from the surface of feathers, skin and hair of animals. Most of these waxes are derived from marine sources. Sperm whales, bottlenose whales. Number one, beeswax as an example taken. It is derived from honeycomb of bees. It contains esters of ceryl myristrate, C13H21, COO, C2, C26 and H53 is a ester linkage, and myricyl palmitate is also C15, H31, COO, C31, 30 and H61 is the formula. The melting point of beeswax is 62 to 65 degrees centigrade. Materials such as shoe polish, candles and paper coating are prepared from beeswax. Spermacety, it is obtained from the head of the sperm whale. It is a rich acetyl palmitate, C15, H31, actually COO, C16 and H33. It melting point range from 42 to 50 degrees centigrade. It is used as a base in the preparation of ointments and cosmetics. Lanolin and wool fats. Lanolin is obtained from wool of the sheep. It's an interesting process. It consists of a complex mixture of high molecular weight alcohol, cholesterol and fatty acids such as carboic, uric, myristic, palmitic, lanoxeric and lanopalmitic acids. It is water soluble and used in the preparation of ointments. When you see the difference between the fixed oils and fats and volatile oils, it's interesting to know, and it is important also here. Esters, the fixed oils and the waxes and volatile oils, the difference. You just see number one, ester of fatty acids and glycerides, that is fixed oils and fats. Volatile oils, they are complex mixtures of hydrocarbon and oxygenated compound. They do not contain glyceryl esters. What is waxes? Esters of long chain fatty acids and long chain alcohols. Number two, fixed oils and fats are thick, greasy liquids, non-volatile in nature. Volatile oils, volatile liquids with characteristic odor, non-viscous in nature. Waxes, they are viscous, non-volatile solid substances. Third, fixed oils are food value. Volatile oils, they do not have many food value. Waxes, they are not suitable for consumption. Fourth, they can be saponified. That means fixed oils and fats can be saponified using aqueous or alcoholic alkali. Volatile oil, they cannot be saponified. Waxes are easily saponified and are saponified only by hot alkali. But there, your aqueous or alkali can be used. But here, hot heating is needed. Number 5, you can see, upon exposure to air, they develop disagreeable odor and taste for fixed oils and fats. Upon exposure to the air, they develop a change in the color and odor and become viscous also in volatile oil. And waxes are resistant to atmospheric oxygen. So example for fixed oils, we have arachis oil, chalmogra oil, castor oil and many. And volatile oil, we know eucalyptus oil, lemongrass oil. And waxes, we have given example in plant, carnauba wax and bayberry wax and animal beeswax and spermacety. An interesting tabular column which is prepared by all the three differences, which makes the students to be conclude for their preparation for their examination. And I think which we have to discuss about most of the drugs also important in the next class. We will just discuss all these 12 drugs are important in lipids and wax. So which we have to discuss in the continuation of the next class. Thank you. We will discuss about castor oil, olive oil, linseed oil, cod liver oil, shark liver oil, cocoa butter, cucumber butter, beeswax, wool fat, lard, sesame oil and chalmoger oil. Thank you. We'll see you in the next class.